lesson for 5.1. This is the kind of applied science section of exponentials and logarithmics. The equations themselves just include the exponentials, but in solving and using the equation, that's when you use the logs. So the equation that we use is P of t is equal to P0 e to the k t. Okay, and what each thing is, P0, we'll start with that, is the original amount. Generally, population. P of t is then the kind of new amount. Still population. Whatever units are the same. Then E is E, of course. T then is time, which is the time that it takes to get from the original to the new amount. Then K is the thing that kind of we have to be a little careful when we talk about its name. We don't want to call it a rate because it's a constant. It does not change within a problem. It changes throughout different problems, of course, but it can be two different kind of things almost. With this sense, if we're talking about population, generally a city's population goes up. It's growing, right? So we would call it a growth constant then. But say we're talking about measuring the carbon in something that in an archaeological dig, right? So the carbon dating, we do that by how much carbon is left, because it's decaying. So it can also be a decay constant. So we call it a growth or decay constant. When it's growth, well, that means it's positive, it's getting bigger, right? Decay, it's negative because it's getting smaller. So this is the equation that we use, okay? How we solve problems is almost a timeline method. So we'll the general sense is just two pieces. It will always start with t equals 0, the starting point, right? And then it goes with P0. And then whatever that starting amount is. That might be given, generally it is, but there's a few cases where it isn't. Then we would have maybe another t, okay? Or we might have a p of t. So, given any assortment of these things, we could also then possibly be asked for k or need to find k, right? Or use k to find something else, right? We can also sometimes have another set of information. Maybe we're given all of these things, right? And then we're given another t. And then another p of t, that's what we want to find. But if we're given all these things, right, except for k, and then we're given the t and asked to find this, well, to find any of these things, we need to have a complete set of everything else. That means we would need to know k to be able to find another p of t. That's why we would be given a full set to be able to do that. We'll see that in an example. So, first, let's just look at an example formula. If we have p of t equals 1000 e to the 2t. If we wanted to look at this, right, and think about what each of these things mean, if we were asked what was the starting amount, well, we know placement right here. So it started at 1000. What is it, a growth or decay constant? Well, it's a positive 2, right? So that means it's growth. What is the growth constant then? It's just 2. We don't include the t, just the number. If we were told to find the population after 2 days, well, we would plug in 2 for t, okay? We would need to make sure that t stays within the same time units though. So if we started out setting up the problem where t was in hours and we were given something about days, well then we'd need to convert. Generally that doesn't happen, but we just need to make sure that it stays within the same units. If we were told to find how long it takes to get to 2,000, well then, a population of 2,000 that is, we can plug in 2,000 and solve, right, for t. And this looks like just something that we've done in 4.4, right, with solving with ease. Okay, so the solving is not too bad, okay? Sometimes the figuring out what we exactly need to do, that's where it gets a little bit more difficult in this section. So for an actual full problem, let's see. If we want to find k, it should be a k, if the population triples every 35 days. So we're finding the population if we're finding k if the population triples every 35 days. So using our timeline, we just have one set, two sets technically, but so we're told we want to find k. So right away we know what we're trying to do. We know we always start with t equals 0, then t equals, well, we're told it triples in 35 days. So that means the new t is 35, right? Then p0, we'll come back to what it actually is, and p of t. Now, we're told that the population triples. We're not told what it starts at or what it gets to, just that it triples. As long as we keep true in the fact that it triples, no matter what we put here, we're fine. So in these cases, always start with 1 for p0. Triples, so that means p of t in 35 days is 3. If it doubled, it'd be 2. If it quadrupled, times 4, right? So it'd be 4. If it halved, right, well then this would be 1/2. So all these different things that you can say, right, we set it up the same way. It's just then the calculation would change a little bit. So let's set it up then. So p of t would be 3 equals p0 is 1, e to the k times t. T is 35, so really this is 35k. Now we just solve for k. So first thing to always do is look to see if e is on its own. It is, because it's just a 1 as a coefficient, so we don't actually need to do anything there. So getting rid of e is next with an ln. So the natural log of both sides cancels with the e. So we have the natural log of 3 equals 35k. Now get k by itself. So we divide by 35. That's what k is. We could leave it there, or generally they'll say round to 2 or 3, maybe 4 decimal places within the problem. Okay, we just have to watch for that within each problem because it may be different within each. Okay, so that is one problem. Another is if in 1990 we have 20.5 million people, and then in 1998 we have 24 million people. This is the abbreviated version of the problem. Basically, then we say in 2011, how many people? So, this year we have this many, this year we have this many, this year, find how many. So, that's definitely 3 sets of information, right? So that means P0 then would be, well, our T0 is actually 1990, right? Because that's our first year. So P0 would be 20.5. Then the next T would be the next year. That's 1998. Well, 1998 is 8 years from 1990. And that means that this P of T is 24. The next year would be 2011. 2011, not from 1998. Always go back to the first year. So the difference from 1990 to 2011 is 21 years. So T is 21. Then P of T, that's what we want to find. That's our end answer goal. So we look at this and we say, okay, we have a P0, we have a T, we want to find P of T. That's not a full set. We need a K. They gave us this so that we could find K. Alright? Otherwise there's no sense in giving us all this extra information. So let's find K first. So P of T, the middle set, is 24. We don't, I forgot to mention, we don't need to include the millions because everything's in millions. It just kind of washes out in the end. So 24 equals 20.5. That's the original, P0. E to the, we don't know K. T to go with 24 is 8. So 8K. And this is just like the previous one. Solve for K. Except we need to get E on its own first. So divide by the 20.5. So 24 over 20.5 is equal to E to the 8K. Then take the ln. Cancels. So the natural log of 24 over 20.5 is equal to 8K. Divide by 8. This is our K. Alright? Because this isn't our final answer, we may want to leave it like this. Okay? Except if it says to round any intermediate answers to a certain amount. Okay? There's, I think, maybe one problem where it might say something like that. So, otherwise, we can just leave it alone. It actually doesn't complicate things other than we kind of have to type it all out into the calculator at once, but it's not a big deal. So, then, now that we have K, we can find our P of T. Should have had that in there as well. So, P of T is equal to, P0 doesn't change, E to the K, well, K is all of that junk. So ln of 24 divided by 20.5 divided by 8 times T, which is 21. We can just type all this into the calculator, okay? We would say 20.5 times E raised to the, it probably gives the raised to you, possibly even a parenthesis. We want the parenthesis anyway, so go with it. Then the natural log of 24 divided by 20.5 divided by 8 times 21. Close the exponent. Okay, so I'm going to do it with my calculator really quick so that we can check our answers. So, took a second, right? But I got that P of T was equal to, let's go to the second decimal place. So I got 31.01 rounded, okay? 31.00662417 and so on, but it rounds to this. So, if we got anything different, right, check your calculation again. Hopefully I did it correctly. Alright, so the other type of problem that we can see that can be a little bit different than this one is if they don't give us kind of numbers like this, they give us maybe percentages instead. So if they tell us in 1947 we had 21% of the C14, how old is the find, like the archaeological find? So then it tells us that the decay constant is 0.00012. It's a long decimal. So they tell us in 1947, 21%. How old is it? If we have a decay constant. So decay constant tells us it's going down, meaning it started, if it got to 21, right, that means it started at 100, right? So anything like that, right, would start at 100, and then we measure how much is left to see how old it is, okay? So that means this is just when it had 21%. It doesn't actually mean anything at that sense to say like, oh, that's not year 0, or that's not our starting point, right? Because that's not when it started at 100. That's just when we found it at 21, okay? So think about our timeline again. T0 is, we don't know when it is, right? So that means we don't know actually how old it is. That's why they're telling us to find that. Then we know we started at 100%, and then we found it at 21%. We're also told the decay constant. So another thing, decay, right, means the K is negative. So negative 0.00012. We have everything written out here, right? We only have one unknown, so we can go ahead and solve. So P of T is 21 equals 100. E to the K is negative 0.00012T. Solve for T. It's just like the other ones solving for K. Divide by 100, and we get 0.21 equals E to the negative 0.00012T. E is on its own, so take the ln. Cancels, so the natural log of 0.21 is equal to negative 0.00012T. Divide to get T on its own. And then calculate. So on this one, we should expect T to be positive, right? It's a year amount. It's just a measurement. It doesn't have a direction or anything associated with it. So kind of a hint to us that it's correct is when we take the ln of a number that's less than 1, we'll get a negative number. Divide by another negative, we'll get a positive. That's why we have to put the negative on that K, otherwise we'll get a negative T. We can just drop it right at the end and get the same correct answer, but it's kind of a good check to make sure that you get the correct solving and type of answer, okay? Because now you know, we use the negative, but then we still got a negative answer for T. So something must be wrong. So the natural log of 0.21 divided by negative 0.0002 is, so T is approximately, this is a really, really old find. So, 2 places again is 13,005 point, rounds twice over then, so 40. So basically 13,000 years. It's a really old find, okay? So this is pretty much 5.1 in the majority, except for one last little thing. When we are doing all of these equations, we've not done anything with derivatives. Okay, there isn't much to do with derivatives in these sections, and 5.2 as well. 5.2 even less, actually, I think, than in this one. But they still use the same language. They still use rates and everything the same, and derivative, of course, as well. There's one little thing though that they kind of talk about that's a little bit different. Okay, so let's go back thinking about our original formula. If we took the derivative of this, we need to think about what's the variable and what's a number. So P0, we know that's a number. K, we know that's a number. T, that's our variable. E is just E, right? So if we take the derivative of this is a coefficient, E to a number times T. Well, that means we use the exponential formula, right? Which means we take the derivative of the exponent, derivative of KT is K, and we multiply it down. So that means the derivative of P of T is K multiplied down times P0. Everything else stays the same. It's just K that got multiplied down, right? So if we look at this, this portion here is P of T, right? So this is the derivative. What we want to talk about is called the differential, okay? So differentials are the derivative, but in terms of what happened to the original function, okay? So that means we'd still write P prime of T, except then we'd just write K times P of T, because that's all we did, was we multiplied it times P of T, right? So this is the differential. Yeah, and then this is the derivative. So when we would want to use one versus the other, okay? They're pretty much interchangeable because they are pretty much the same thing, right? It's just sometimes one is a little bit better than the other. So if we're told to find the rate when the time is 35 days, well, then it's better off to use the derivative because it has a t in it. This one doesn't have a t, it has a p of t, right? So if we are given a t, we want to calculate using this one. However, if we're told to find the rate when the population reaches 2,000, well, then that means we actually want to use this one because we know the population. Okay? So otherwise, if we didn't use the differential, we'd have to say, okay, well, going by our original, then find t. T is something, right? And then plug into this. That's multiple steps that we don't need to do. It's a very, very easy calculation otherwise. Just times t. Okay? So that's a differential. That's 5.1. 5.2 is pretty much the exact same stuff, just kind of a little bit different because it's the exact same formula. We just use different letters, okay? Because it's the letters that we're used to for this. This is compounded continuously. Alright, so we've done this in college algebra, maybe sometimes in high school in different places, okay? So it's the A part equation. A equals PE to the RT. So P is the principal amount of money put into an account at a certain time, right? So usually right at the beginning of when you open the account or just when you're documenting for the problem. A is the new amount. Again, it means the same thing. Principal is the original. It means the same thing as last time. This is just P0 in a different sense. Then T is still time. R though, R is not growth or decay because hopefully when we put our money in an account, right, it doesn't decay. We don't want to lose money, right? We're not putting it into the stock market with this, just an interest rate account. So that means we'll gain always. That means it's just positive, so we just call it interest rate. Do not confuse this rate with derivative. This is just interest rate, right? We also need to remember to put it into the decimal format when we put it into the equation, okay? Because otherwise we'll get weird numbers for answers, and we won't be able to figure out why because we're doing everything correctly. Just make sure to convert from percentage into decimal. So the only one of this that is kind of worth doing that is any different than what we did before is if they tell us the present value. That's the type of problem it is. So, takes a second to kind of write this one out. So we want to find the present value of $7,000. It's payable at the end of 2 years. Let's see, if the interest rate is 7%, and that's enough. So, I shortened it a little bit. But essentially what they're saying here is we need to find the present value of $7,000 at the end of 2 years. So, $7,000 at the end of 2 years. Present value is now $7,000 at the end of the 2 years means what do we got to put in the account to get out $7,000 if we leave it in there for 2 years at 7% interest rate. So, timeline again, right? We put in, we don't know. We get out $7,000 at an interest rate of 0.07, decimal version, remember, t equals 0 and t equals 2 years. Find p. Put it into this formula. Just the same thing. Doesn't matter that it's a, different letters or whatever. So, a is 7,000 equals, we don't know p, e to the r is 0.07 times t is 2. Simplify the exponents, so 7,000 is equal to p, e to the 0.07 times 2 is 0.14. Now, we want to solve for p. We solve for something when it's multiplied like this through dividing the other thing out, right? So we need to divide by the e to the 0.14. That means p is equal to $6,085.51 approximately. And obviously, since it's money now that we're talking about, you pretty much always round to 2 places. Unless they specifically tell you otherwise, just assume round to 2 places. So, that's 5-1 and 5-2. That's it, pretty much.